So thank you very much for inviting me, giving me this opportunity. So let me make it clear that this is a talk on math pedagogy, but it's only school classrooms. I'm a researcher at the Institute of Mathematical Sciences in Chennai in India, and I got quite interested in undergraduate mathematics education at a very early, couple of decades ago really. But then it took some digging and started doing, and then I felt that the problem was really in the high school, and I started interacting with high school teachers, and then I realized that the problem was much further down, and so then I was working with school children, primary school, middle school children and teachers for a long time now, and those are the experiences that I'm going to talk about. So I apologize that this is not about higher education, but I think I have been teaching in adult education classrooms as well. And I find that there are like undergraduate classes as well as graduate classes. My typical classes have at the university have PhD students and graduate students. So, but I find that there are like some common problems all along. But the issues that I'm going to highlight are mainly from middle school math pedagogy and only mathematics. But again, I think there are some common lessons for classrooms and many things. So let me see if I can sell some of these ideas to you. Now let me see first if I can figure out this guy. Okay. Yeah, so I was once speaking to some children at a math club, and so the idea was to get them to do some math projects. And children were used to doing science projects, but thought, how do you do projects in math? You do problem solving maybe, but how can you do projects? And I was trying to convince them that math projects could be fun, and I was giving this pitch that math is there every day, in everyday life. And, there is the standard pitch that you tell children that, you look around, wherever you see there is a lot of math. And, well, this is what I was trying to do. Well, where do I click? Some directions work, so I have to. Okay. So at that point, a 13-year-old boy called Naveen, he came to me and he said he liked math very much, would like to do a math project. I was very happy. And no, you, no? So who is the one who is going to get me there? Or is there a page down here that I can? Yeah, I think this is the simplest thing. Okay. So then he told me that he liked spiders very much and said, how about a project involving math and spiders? Now, this is a classic case of putting your foot in your mouth. I had just been saying that, math in everyday life, wherever you look, and the guy says, let me do math and spiders. Only kids think of something like that. And so I had to do something on the spot. So I told him, how about the spider's web? This is the only thing I could think of. I said, you think of spider's web as a sequence of concentric hexagons radiating from the center. So there is this nice picture. You can study it. And then that's it. That was the interaction. Then about a month later, there was this math expo when I went, and the children were all presenting projects. The teacher had been interacting with the students. The teachers had been interacting with the students. So there we have these math expo, which is really a nice thing. And the children are demonstrating what the projects they had done. And then I saw this Naveen's project, and it was something amazing. So he studied this, and he did all sorts of things. I mean, he came up with formulas for perimeter and area, because these are the only two things that you learn, about pictures like this when you are 12 or 13 years old. And so he came up with some formula. He had no idea what these formulas would be used for or anything, but he had his formulas and he could show how to calculate it for different things. And then there was something very interesting that he did. He tried to give a procedure for the shortest route by which, see, spider is at one point and insect is at another point, and only a child would worry about how quickly a spider would get to the insect. Spider couldn't care less perhaps, but anyway. Thing is, he had no idea about coordinate systems. He didn't have Cartesian coordinates in his head, and he had to find some way of talking about how the spider would find the thing. So he actually came up with a procedure, and it was really amazing to me. So this suggested to me that, there are like these kind of concepts that we tend to think of as higher mathematics, hardly part of school curriculum, middle school curriculum for sure, and he was having all these ideas. And he was intensely frustrated that he couldn't give a formula for this, because to him, doing math meant giving a formula, and he couldn't give a formula for this, and that was frustrating for him. And it was worse because, well, you guys live in such beautiful rooms. So, in India, where I come from, there are a lot of places where you go, you see spiders' webs around. So, hey, come on. And you see them in, where do you see them? You see them in corners, right? And in corners, the spiders' webs never look like that beautiful picture that I drew. They're always pulled, right? So these are, concentric hexagons, all right, but they're like pulled in one direction. And so he knew that. And then he realized that once the picture is not exactly this nice regular structure, but irregular in particular ways, like I said, it would be a hexagon but pulled in one direction. So the concentric ones also get pulled. So he drew pictures of these, and he realized that the formulas that he had will not extend for these. And this was a matter of great frustration for him. He wanted to know. And again, he didn't have enough trigonometry at this point to be able to give a trigonometric function describing it, or function anyway. So you don't expect it from that, but that sense of frustration he felt was very important to me, because, he was going after a mathematical concept, and I thought he was a mathematician, right? And so he filled notebooks with figures showing what happens when you pull one corner of the web, and as I said, he was very frustrated. He actually wanted to calculate the amount of goo that would generate, one given web, okay, and he didn't have enough physics to think of notions like tension and so on. But in fact, I invited him to our institute to give a seminar for our mathematicians. So our institute is Mathematics Research Institute, so for the mathematicians to see one mathematician at work. And well, now the point is that there are lots of Naveens around, right? In fact, every school teacher has seen many Naveens, and every classroom has some children of this kind. And is there any classroom process that can talk to these children? Well, okay, so here are some examples. Now, here is a game. This is really a childish game, and I think of a number, and you're supposed to find what it is, right? How many questions do you need to find the number? Number between 1 and 100, 0 and 100.
Log of that.
No.
Why not?
One question should do. I didn't tell you, right? What kind of answer? So you asked me what is the number, I would tell you. So, okay. So you have to think like children, right? Okay. So and then, okay, we make it more interesting and say, I'll give you only yes or no answers, and you try to find that thing. Now, when you play this game, of course, you have computer scientists, and immediately you say, log n, right? And but with children, now there is this space that you are searching for, and the kind of questions they ask. One child will ask, is it a prime? You say yes, and then another child asks, is it divisible by 3? And this one is going to scream at him, saying that he said it's a prime, right? Or is it divisible by 4? You say yes, and then somebody else asks, is it even number? And somebody else. No, this kind of interlearning that happens is extremely important. And we tend to think of question answering in classrooms as, I need a clarification and I ask. And but there is so much else of learning that is going on. And a game like that, and especially when you play with children, one group thinks of a number, another group thinks of ask the questions. This is really nice, because you don't play this game only to find the answer in log n questions. You also want to ask, can I force you to ask log n questions, right? I mean, with 100 numbers, can I force you to ask 7 questions? How do you get kids to think of that, right? So when you play it in 2 groups, you say, look, you want to make it really hard for them. What number are you going to think of? And I tell you, the children go through a lot of effort. 50 is a very popular thing. 99 is a very popular choice. 1 is a very popular choice because they think that extremes are always going to be difficult to search for. Then you point out, what if somebody asks, is it 99? Then you are dead, right? So, and then it takes a lot of discussion, and I found invariably that children almost never come up with this thing that you don't think of a number at all. No. So I think that's an adult one. I mean, if I say that, they say, oh, that's cheating. But it's not cheating. I say, I don't think of a number at all. You ask any question, I say yes or no. If you divide it into unequal parts, I'm going to say whichever answer which gives the bigger one. And if it is equal, I'll just randomly pick one and say, arbitrarily pick one and say, and I keep track of the answers. By the time they understand the strategy, right, that I have a way of forcing you, no, not only that you have a strategy to find the answer in 7 questions, but I have a strategy to force you to ask 7 questions, and this is like tight, right? This understanding, when it comes up, is a real revelation. When there is a moment out there that you see, there is an aha moment out there, right? Not for all children. For some children, surely. And then they immediately start thinking about what happens with 1000 numbers, when it's 3-digit numbers. Log n is harder. I mean, it depends on the age group that you are talking about. To think of it as a function that grows in a particular way, and think of log n to the base 2, taking ceiling, that's a bit much. But the fact that children can go this far shows that, we really underestimate them very often in our classrooms. And this is because if we take, so my main point, I'm going to, keep coming back to it again and again. If we think of mathematics as algebra, geometry, trigonometry, calculus, whatever, we miss a huge amount of ways of thinking that I think our students are capable of at various levels, and we miss them. So here is one. So here is another, which I'm fond of. This is not a game. It's an argument. Now, this funny thing called root 2, right? You come across it in middle school, and children learn the proof that root 2 is not rational. And this is part of all curricula, which is a very nice proof. But then, does it exist? Okay, it's not rational. It's like saying it's not an elephant. I mean, it's not a, but what is it? So, invariably, if it's with school teachers or children, I ask, what is root 2? 1.414. Well, it's not 1.414. So, what is it? Because, you have a calculator, you plug in 1.414, square it, and surely it's not 2. So, what is it? And so, I find that I've had this kind of arguments and discussions many times. At some point, somebody always says, if not in these words, it's the length of the diagonal of the unit square. You take a unit square, take the diagonal, and the length is, but what is length? What is length? I mean, it's an intuitive notion. It's okay, but what is length? Oh, length is, something in centimeters, something in meters, whatever. Okay, that's okay. But then, what is root 2 centimeters? Show me root 2 centimeters. Show me a unit square, a unit 1 centimeter square. Okay, but then that's a problem. But everybody knows that already, that the moment you try to measure it with a scale, you're never going to get very far. And now it depends now at this point with some amount of stimulation, some amount of discussion, some amount of argument. Somebody says it's not a recurring decimal, right? It's actually not 1.414, it's 1.414 something which goes on forever. How can it go on forever? How do you know that it goes on forever? I mean, I don't believe it. I usually take the stand that I don't believe it. I mean, it doesn't exist, right? The real line. See, the thing is, by the time we are talking in high school, children know the real line. Then the number line is something they are very familiar with. The number line, rational points on the number line, they are very familiar with, and they know that there are these dark areas between the rational points. They know pi. There are all kinds of things sitting inside that, and which are represented by infinite decimals, because the curriculum gives you all this. But then, what are these things? How do I find one, right? And square root of 2 is 1, something like that. And I've heard children or teachers say, okay, it's the solution to x squared minus 2 equals 0. Very nice. But what the hell? I mean, you just redefined it, right? I mean, then how do you didn't show me that a solution to that equation exists, right? It must be somewhere on the real line. I don't know. What would be your argument? How do I find out? How do I show that there is, it must be a point on the real line, right? It's one single definite point on the real line, right? How do I find it? Or does it matter that I don't have to find it? Can we do all of school mathematics? I mean, come on. We do not just square root of 2. We do square root of 2 raised to the square root of 2, right? I mean, we do all sorts of things. Is it not important to find it? Should one, I don't know, what do you think? So, yeah, I would like to hear. Yeah, Nadia?
I think this is what the Greek debate of rationality. That's why they call it irrationals. Because you can construct it in the geometric model as you described, right? I can draw them with lines of compass.
Paper folding.
Yeah. But I cannot represent it by my natural numbers.
Yeah, but the point is that the real line is critical for curricula, right? Remember that we are very far from the Greek age. I mean, our students have to do calculus as a compulsory subject,
but
right?
That would take the position the real line is just a model. It doesn't exist. I agree with you with that.
No, I haven't said it exactly. I believe. So I'm talking about the argument, right? So the thing is, the way it proceeds, right? I mean, okay, we don't have time. I'm just giving you ideas for the kind of, arguments and discussions. And, in some sense, the point I'm trying to make is that a math classroom is as much a place for debate as, a literature classroom, right? Because, see, I'm talking about it from the student's educational experience. Because if you go to the humanities, you get, especially literature, poetry or whatever, there are debates, the classroom is like this. Math classrooms, dead silence. I mean, the squeak of chalk on the board and the rustle of paper where everybody is dutifully writing notes. And so I'm talking about breaking that. I mean, and I'm pointing out that there are lots and lots of topics for arguing, debating between sensible people. I mean, it's not just some emotional argument that we are talking about, but something that's intellectual, right? And so, for instance, with a calculator, this thing is typically it moves very fast because, you realize that 1.414 squared is less than 2. Okay, so you try 1.415 squared, it's more than 2. Okay, so it's somewhere in between. So let's try 1.4145 squared. With the calculator, you can see. So you keep going, and actually you come up with an algorithm, by the way. It's very easy. With middle school children, you can do that, having got the expansion up to n digits, calculating the n plus 1th digit, you get an algorithm, and you know that it's going to go on. So the idea that it goes on forever gives a very precise meaning, and children understand that you get an infinite decimal, and you can complete it. But comes the question, well, if we do all this, where are we left? You get this infinite decimal, so children would say, okay, take that and square it, you will get 2. Wonderful. But how do you square infinite decimals? How do you multiply infinite sequences at all? The only algorithm we know for multiplying is for finite sequence of numbers, right? So how do I do it for, if I have one infinite sequence and another infinite sequence, how do I multiply? Why should it work? Because you remember that there is this problem with the carry, right? The carry keeps moving right. How do you know that the carry will go on forever? Okay, there's a little theorem there that tells you that the carry actually travels only a bounded distance. And that's a new thing that they learn. And it's something you can do with children and prove. And in fact, you can show that here is one algorithm that if you can set up an arithmetic with infinite decimals and actually, do operations on them, multiplication on them. And what you get is sadly not 2. What will you get? 1.999999, the infinite sequence. And at that point you say, boom, we call it 2, right? 0.99999, we call it 1, right? That's an axiom, if you know axiomatic development of arithmetic, you realize that, for the reals especially, there's no hope. There's no other way. You can only axiomatically insist that. Now, I'm not saying that all this is absolutely important to put into curriculum and so on. I'm just pointing out that a thread of argument can actually can navigate pathways by which the kind of remember the Naveens, the kind of challenges they need, right? That there is so much that this can offer. So this is an example of that. Now, I'm here mainly to give lots of examples. Okay, so this is one very specialized kind of interaction that I was talking about. But what are normal classrooms? All our normal classrooms, how do they go? I mean, you have some particular syllabus to transact, and that day, you have a particular talk on that, and something happens. Right? So here is one. Again from middle school. So as I said, somewhere in India, someday, it could be anyway, a mathematics hour in an elementary school, class 7, Mr. Garg is teaching chapter 14, areas of rectangular paths. I think all schools have this this one. And so here is, so let's say that he actually gives, you are supposed to motivate by giving practical problems. So it talks of fences around rectangular gardens, and you already have formulas for areas for squares and rectangles, and therefore, in fact, you can think of all these pathways as one rectangle inside another. So you have area for this, area for the other, subtract, blah blah. So draws, I said squares, so anyway, and this is a reasonably convincing thing. And then he gives an exercise. I mean, this is all from the standard, our NCERT textbook that I'm talking about, and walks around, and children are writing in their notebooks. No, this is the kind of scenario that we see in classrooms. I'm saying somewhere in India someday. I mean, I think this is something that I can say anywhere in the world. I mean, this is a problem, this is there in pretty much every math textbook and a problem. And maybe the teacher doesn't walk around in this particular way, but something like that happens. And then there is this Neeta, she's looking very troubled. And she says, sir, what's the perimeter of the path? This path going around this garden. And because remember that class, these are 12, 13-year-olds. Area and perimeter are their only introduction to this whole world of reasoning with these objects. And so he says, oh, only curves have a perimeter, lines. A path is a region, so it has no perimeter. Now, this is precisely the way we answer kids, typically in math, right? Now, what is the sense of this? Okay, there's, and but she's not satisfied, right? Having a photographic memory, she recalls her class 6 textbook, defining the parameter to be nothing. I mean, this is a quotation from, as I said, from this book, right? Nothing but the length of the boundary of a region, right? Now, the boundary of a region is a curve, and that's what he means. But here, remember that children are getting all these kind of learning from different years, different contexts, and somehow we build this coherent body of knowledge or system of understanding that we call mathematics out of all this, right? And she's really troubled. Now, it's very difficult for him to answer at this point. And in fact, I have no idea what he does, but usually a teacher would say, no, that's not right, this is right. And somehow children also would be happy to believe that class 6 is wrong and class 7 is right. Right? I mean, it's supposed to grow like that, but in any case. So here is another classroom. And here is a problem, and this is a challenge on the blackboard. It says, okay, I give you 64 meters of fencing with which you can mark off a portion of the school playground for the exclusive use of class 7. Area is called C7. Now come up with plans, right? Which plan gives most play area? Which plan is best if it is going to be used mainly for running? And which plan do you like best? And, children sit in groups and work out various plans. Question is, who has the right answer? Right? Now, there's no right answer to this, right? I mean, this is a very different one, because this is also a problem in the class 7 textbook, but it's not posed in this fashion. The problem is posed as, if you have 64 meters of fencing, find the shape that maximizes the area with this perimeter. Not exactly in this form, but it's a very different problem, and that has a unique right answer, but this does not have one right answer. But the process, this is what I mean by process here. The processes that go on into this is something not only engaging children, there is a possibility of discussion, there's like so much more that can happen. And of course, you know, among rectilinear shapes, that the square maximizes area is something that children have to get to, right? Among curves, the circle maximizes the area is something that the children should get to. But it's not something that you bang impose on somebody. You know, when you do that, you know, 3 children will get it and 27 children are, you know, waiting for the bell to ring and drop out of the entire class. But something like this can actually engage a lot of children, and, you know, many children then participate. And this is, you know, an example that illustrates this. Okay, so the kind of vision that I am talking about is that you want children to enjoy mathematics and they learn important mathematics, because I think there is a fair amount of trivial mathematics that happens in our books, in our classrooms, and all the way. I mean, I think it's, you know, without exception. I mean, I would put it all through graduate school as well. And for children, it's all the more important to see it as a part of their life experience, and then pose and solve meaningful problems. I actually found a textbook, you know, and a primary school textbook in India, which actually had, if in a garden there were, I think something like 26 goats standing in the garden, how many legs are there? Now, unless you are a butcher, why would you be interested in counting legs of goats standing in the garden, right? I mean, and another problem I saw was, if mother made 152 puris and in a family of 12, and everyone ate an equal number, how many will be remaining? I mean, come on. Poor mother. I mean, 152, that's the only reaction children should have at that point. And say, what kind of a family is it in which all people eat equal number of puris? I mean, come on. A bizarre family, right? That's a meaningful reaction, not calculating and doing remainder. So that's what I mean. And these kind of things, I mean, well, in my higher secondary class, I had a teacher who wanted to make this point about, you know, he would have problems, a physics teacher, he would have problems like, consider a massless elephant tied to a pulley of mass m with a rope, distance k. I mean, just to rub in this point that when physicists say massless, they mean massless. It doesn't matter what it is, right? Okay, you can do that as it, you know, to make children laugh, but somewhere, you know, these should be, so meaning I'm trying to say is in the head of whoever is doing it, not, you know, so there should be some meaning to what this thing, and math is notorious for these kind of meaningless problems. I mean, physics I gave an example, but math curricular and math textbooks are full of really meaningless problems. And I'm not saying meaning by relation to external world. I don't care at all. It could be pure abstractions. It could be some very abstract objects, but very meaningful. And this, I think, is extremely important for children, and ignoring that is perhaps one big reason why math is considered alienating. And children pose problems. This is the other one, that children are used to only solving problems given by adults. This idea of constructing problems, posing problems for each other, and children come up with very delightful examples, and that's another one that I would say. And children use abstractions to perceive relationships, to see structure, to reason about things, to argue. And this is, I think, an extremely important thing, because I'm not talking about proving, like with the root 2 case, doing arguments, arguing about something, right, that this is true, this is false. And I've seen with primary school children, you know, something like starting with, you know, if I multiply 2 odd numbers, what I get is an odd number. Doesn't matter how big. Now, you know, arguments for this, you know, they're trying to convince that, you know, when children talk like that, I think quite a bit of the problem with math disappears. At least is what I would like to say. And really, the last is very important. Teachers expect to engage every child in class, and I should say not just child here, student, right? Because this is a problem, whether it's undergraduate class or primary school to graduate school is the same thing, right? I mean, Vlad, we were discussing that. I mean, there is a sense of frustration that you have when you walk into a classroom and you don't expect to engage all the students in your class, right? Now, I think one would think that for pedagogy or, teaching learning processes, this is something important. What does the teacher feel when she walks into the classroom? Do I expect to engage everyone? Or when I walk in, I already come with an expectation that only 1/3 are going to get it, 2/3 are not going to get anything at all, right? Now, what kind of a classroom is that? I mean, if we get used to that as the norm, across schools and universities, something is really wrong, I think. And in math, I certainly feel that this is a very serious problem because, I've done lots of teachers' workshops, math teachers, across the board. I mean, from, as I said, from primary school to graduate school, invariably most math teachers say, look, I expect, about 1/3 to get it, and I feel happy if it's about, a little more than 1/3. In practice, it's closer to 1/4. And another 1/3 I know is not going to get anything out of the course. But something is really wrong with what we are doing, right? So, and I'm saying that unless it's part of our vision, rubbed in reviews and everything, we are accepting something that's not right at all for educational processes. So, the content areas of mathematics are very clear, school mathematics especially, arithmetic, mensuration, algebra, geometry, trigonometry, data analysis. I'm not quarreling with any of that. I mean, I think that's it. And but what about the processes, right? Use of patterns, visualization, use of heuristics. I mean, this is a big, well-kept secret that mathematicians use heuristics, right? In school, there are no heuristics at all. There are only things that work, right? Formulas. And when Naveen's looking only for formulas, that's because he's indoctrinated, right? Estimation and approximation, right? And, in primary school, you need to estimate quantities. You need to estimate measurements. In high school and in graduate school, you have to approximate terms, right? You have infinite sequences. You need to know whether it's going to converge within 20 terms, how fast it will converge. Now, you can't do science at all. In fact, you can't do physics at all and chemistry, in my opinion, if you're bad at estimation and approximation. But that's a mathematical skill. And it's the job of mathematics to give you this ability to estimate various kinds of things. I mean, and making connections, right? This is very difficult for children. I mean, do I use algebra? Do you use geometry? Is it trigonometry that I use? Actually, no. You want to solve problems. And of course, children learn quadratic equations, but when they see, m1m2 by r squared, which they see routinely in physics, no graph pops up into their head, right? I mean, this is nothing to do with quadratic equations, right? So these are very different things. And one child actually taught me something very important. I mean, I was helping her. She was quite a bright student, and she was preparing for school finals. And then she said, Jam uncle, sine theta, if it comes in mathematics, it's the ratio of side to hypotenuse. If it comes in physics, it's a wave. Well, very nice. So, and nicely compartmentalized thing. And it's smart. I mean, that's the only way to prepare for exams. At that moment, you don't start, board exams, you don't. But that tells you, you see, that, and formal communication. And why is it that mathematicians love jargon? It's a very stylized language, deliberate stylized language, and that's important. And I think that's very important for all math and science learning, that you need formal communications. And many children get left out of the game when they don't realize this, that science and math are about very formal communications, and it's like learning language, a new language to speak in, and if you're not fluent with the language, you're going to be left out. But we don't talk to them in this thing, and don't give opportunities for learning the language in itself. And okay, so but these are examples of processes, and all I'm trying to say is that somehow we have to build this in. There's a quote which I like from William Thurston, where he says that the task of a mathematician is to increase human understanding of mathematics. Well, Well, a mathematics curriculum has both logical structure and a pedagogical structure. And the fact that both are there is very easy to lose sight of. And the analysis of the first is a mathematical task. But what about the second? Well, the second is the task of mathematics education. Now, but then we need an analysis of curriculum that is simultaneously mathematical and pedagogical. And I think even at higher secondary level, right, we lose sight of that. Maybe at primary school, elementary school, there is some awareness of that, but we very quickly lose sight of that, and I think that's one of the big problems that I find with this. And that's what I call pedagogical maps. You know, we really need pedagogical maps of the mathematical terrain. So it's like there is this terrain that you need to explore, but you need maps, you know, you need pointers, you need various ways of looking at it. And usually, you know, Atlas is not one map, a whole lot of maps. I mean, like physical maps, political maps, various kinds of terrain maps, and we need that. And so just to say what do I mean by these two things? You know, if you take a polynomial, right, most students that I have met don't distinguish between just writing a polynomial or a polynomial equation of the form y equals px and px equals 0, right? I mean, they, you know, in high school you use all these things interchangeably. Well, what are these things? We ask students to factor polynomials, we ask students to expand them, so they are expressions, right? So they are expressions in an expression language. We ask students to graph them, right? So they are functions. So, and we ask students to find their roots. We go find the root of the polynomial, right? Most school textbooks you see will not say, write the equation, no, so find the root of the polynomial. So they are equations. What is the mathematical answer? It's not an expression, not a function, it's an element of a ring. There are many expressions for it, certainly not a function. Now, I think it's important to be aware of both, and that's what I'm trying to say. This is the mathematical answer. A pedagogical answer is it's both an expression and a function depending on the context and the level of the student. And I think this maturity of dealing with content and what happens in a classroom and not take either of these in an ideological, fanatical way, but to move back and forth, you know, is I think extremely important. And this is an example I'm talking about in terms of this, you know, what I mean by the pedagogical map of the terrain, right? And there are lots and lots of examples of this kind. So by mapping, I'm really talking about reconciling the two answers. And if you start looking at the content, there is like, you know, hundreds of such places. Now, perhaps the biggest experience discontinuity for students is in the epsilon delta definition and questions that I never asked. I mean, like the one that I raised a moment ago. Why is 0.999 equals 1? What are we assuming here? What if I don't equate these? What part of mathematics will go wrong? Can I do calculus? And by the way, there is a question one student actually asked me. And, sir, if I don't have this, will I get all these things? You know, I said, look, the only way you can do it is by going to logic. You know, there is a formal logic. There are people who have done these things. And the axiomatization of reals is extremely hard. The only ones that we know use this as an axiom. Well, but what about something like this? What is pi squared, right? Well, it's the area of the square with side pi. Well, that's nice. But in general, I mean, we have all this kind of stuff, right? I mean, remember, children are taught multiplication is repeated addition, right? And the kind of additive reasoning is very different from multiplicative reasoning. And this transition is not easy for children to grapple with at all. And you can't come up with algorithms like that and then understand, you know, if you think of finding powers as repeated multiplication, you have a problem when you look at pi raised to the e, right? There's no hope of doing something like that. So how do I understand all these things, right? You need to look at notions of scaling, you need to, no. So, and these are algebraic notions, and what I'm trying to point out is that algebra, as we learn, you know, emphasizes expression languages in a particular way, but the underlying geometry is something that's, you know, highly glossed over And of course, the children who learn those things are the ones who become very good at mathematics, but I'm trying to point out that there are like basic problems. Like for instance, this is a very fundamental thing with primary school children that I keep coming up with. It seems reasonable that dividing a ribbon of length L among 3 persons should get L by 3 units for each. But what about cutting it up into pieces 3 centimeters long, generating L by 3 pieces, right? You can't do that. I mean, there is this all the ceiling and floor that come because the number of pieces is an integer. It's a whole number. And now there are like, I'm just trying to say this is all to do with notions of continuity that are there all along. And somehow we gloss over a huge amount of this and suddenly hit kids with, the continuum. And of course, the discrete is something that kids don't understand at all. And the transition from high school to undergraduate math is it's a double discontinuity according to Felix Klein, because, the discrete is very natural, but somehow by the time you finish school, it's only the continuum that you understand in this sense without seeing this relationship between these at all. And, you try to learn a bit of analysis and then combinatorics hits you. So, you are left with a great disadvantage. At least Felix Klein has a very nice article on that. Anyway, so I would say the big difference is problem solving. I think in all this, what is the final thing? Where is the way by which you can bring in all these processes? Well, problem solving in the sense of polya. The answer, if there is one, is not the end of a process. And we need to make a shift from getting answers to gaining insight or constructing arguments, right? And for which, what kind of problems are good? And okay, so I would say that this is this really big difference between school mathematics and the discipline of mathematics. And what do I, by the difference? Well, maybe I should just quickly say this because, in most mathematics classrooms, problem solving only means end of chapter exercises, right? Now, end of chapter exercises are to illustrate specific curriculum material put into the chapter, right? That's not problem solving. Well, you can call this problem solving for learning particular mathematical content. And I mean, I did my undergraduate degree was in electrical and electronics engineering. And, we did enormous problem solving. But most of it was of this kind, right? Fourier transforms, Laplace, you learn a huge amount of content, and for that, to illustrate that, to get you familiar with that, good problems, and I would say we have very good textbooks on these. But what about learning problem solving? What kind of heuristics do I use for problem solving? When do I use analogies, right? When, Polya says, draw a picture. Doesn't matter what a problem is, right? You are given a problem, first step, draw a picture. I thought it was a beautiful thing. Actually, it makes sense. We do it when we do mathematics, but, and I mean, there is a whole lot of strategies out there. But then there is this important thing, which is really what I'm interested in, is learning mathematics through problem solving. And that's what Polya used to talk about as well. So which means open-ended exploratory problems. And these are very rare in mathematics classroom. And I'm here really saying mathematics classroom to mean, computer science classrooms, many engineering classrooms, whatever. And then this is also very important. And I think the Naveen thing was, the spider project was also to talk about this, that big and small problems, solutions that require different durations. For children, it's very important because when you come out of school or even undergraduate class, problems are all those which take 10 minutes to solve, half an hour to solve, maybe an hour to solve, not days to solve, no? And we must dispel the myth that any problem that cannot be solved in 5 minutes or half an hour or whatever is unsolvable, right? And this I actually did as a poll, I remember, in our university I was doing, but there are like 200 students, undergraduate students. I tried to say that, here's a problem that I tell you that so many people, clever people tried for, 5 days and couldn't solve. What do you think? Unsolvable, no problem. But that's because they don't have, how much experience do you have as an undergraduate where you actually grappled with a problem that takes, a very long time to solve, not just individually, 3-4 people together. But such problems don't exist. Of course they exist, right? And of course, open problems. The fact that there are problems which no adults have been able to solve for centuries and yet may be solved by someone in the future tells the student that mathematics is alive. And that culture of open problems is what, keeps mathematics alive. And this is something I think we have to communicate with children. Now, there are examples for and the activities that we can do. I'm going to skip all that. And so one more thing that I want to just mention before I conclude is that, this, as I said, since I had an undergraduate engineering education as well, right? Now, certainly in math education and in engineering education, I find this conflict, which is a serious conflict, but, there on one hand, there are procedural skills, and on the other hand, there is conceptual understanding. And we need both, right? We need, you can't learn calculus and look at problems on, surfaces, something is moving, generating a surface, you want to calculate the volume. At that point, you can't be sitting in, doing real analysis in your head, doing, no, you need certain procedural skills. So, certainly a whole lot of mathematics demands procedural skills, certain amount of conceptual understanding. I think any fanatical way by which we say, oh, procedural skill is all nonsense, you only need conceptual understanding, I think it doesn't work. But what of course happens in most, this is a backlash against the usual classrooms, which don't go into concept at all, but elevate procedural skills to a great important thing, and therefore but I think this is not right at all. We really need a great blend of the two, and my sales pitch is that it's only by looking at the processes involved you will be able to get a handle on both. Now, there's a lot of argument on this. I'm going to skip this whole thing with examples and argument on factorizing polynomials and so on. Okay, so let me get to the main point, right? For me, and not for me, I mean, this is for most mathematicians, if you ask, what is doing mathematics, right? Doing mathematics means things like this: selecting between different representations, devising new representations, looking for invariances, looking for lots and lots of cases and seeing what's common, observing extreme cases and typical ones to come up with conjectures. Now, this is a very important thing, very unique to mathematical training. Looking actively for counterexamples. I mean, this is a big secret kept from our students, that when you do mathematics, you don't look for proofs, right? I mean, I don't know. I mean, I think whatever work I have ever done, right? When you think of something, you look for counterexamples. The first thing you look for, as I said, actively, is for counterexamples to get yourself wrong. And it's by searching for counterexamples and finding that you're eliminating ones that you've thought of from your experience, you gather more confidence in the assertions that you've got, right? Now, this is a process that school children don't see at all. And undergraduate students, if they are lucky, get to see it in a couple of places. It's only graduate school that you see this at all. And then, this is something that's unique to mathematics. You're doing a problem, it's hard. What do? You generalize it. Now, this is something unimaginable in most domains, right? A specific problem is hard to solve, you generalize it, it becomes simpler, right? And building on answers, this is perhaps, I think, critical to mathematics. Building on answers to generate new questions for exploration. Now, and so on, and I have a few more, but I would say that these are processes that, I don't know if these are axioms that characterize, doing mathematics in a complete way, but, they're sound axioms, and no, so I must say that I'm very proud of this list because, in the ICM, the International Congress of Mathematicians, in a panel on math education, I was talking about it. Timothy Gowers was the chair, and, he put it on his blog. Gowers' blog is one great thing for math people to look at, and said, hey, do you guys like this list? What do you think? And Terence Tao wrote about it, and so then this list is now, expanded, and a lot of people have looked at it. And so I'm trying to say that many serious mathematicians are willing to say that this is the kind of processes that are important for doing mathematics, only for that. But the main point is that these are missing in our classrooms. I have put school, but I would say these are missing in our undergraduate classrooms, my MSc classes that I am involved in. And so what can one do? So this is perhaps the summary of this, right? A typical classroom are preset exercises really conducted on the blow of a whistle, everyone going through the motions. I'm sorry, that sounds very pessimistic, but and interaction between students as well as between students and teachers is essential for encouraging the processes listed above. If if it's that deathly silence, then this kind of processes cannot come alive at all, and curriculum needs to be shaped so that all these kind of processes can actually be emphasized in the classroom. And can assessment take note of processes? We don't know. And I think this is within the realm of feasibility, but we really need this shift in content to process. I think I should conclude, so let me just skip all this, because it's all polemics anyway. Okay, so see, an emphasis on process goes with a multiplicity of approaches. Like the problem with the fencing that I was talking about, there is no one right answer, there are many right answers. This is crucial because I call this the tyranny of the one right answer, found by applying the one algorithm taught. This tyranny is perhaps the single major problem of fear of mathematics among most children, that math and science, any quantified ones. That in humanities, when I do social sciences, I can always write different things and get away with it. In math, there is only one right answer, and if I don't get it, I'm screwed, right? So in general, when we have many ways are available, one can compare them, decide what is appropriate when, and in the process gain insight. The theory of algorithms has worked mainly that way, and I would say appreciating the richness of folk algorithms, what people use out there in everyday life, in when they construct buildings, when they do various things, I think that can actually accentuate this perception. Okay, so here is a quote again from William Thurston, where he says that the long-range objectives of mathematics education would be better served if the tall shape of mathematics were de-emphasized. This tall shape it's tall and spindly if you look at it, our math curriculum, because you learn arithmetic, you learn decimals. If you are bad at fractions, you have a problem with decimals. If you are bad at decimals, you have a problem with algebra. If you have a problem with algebra, you're going to have a serious problem with trigonometry. And if you have a problem with both of these, you're screwed in calculus. And if you are undergraduate education, a big amount of it with differential equations, you have a big problem, right? So he says we need to de-emphasize this by moving away from a standard sequence to a more diversified curriculum with more topics that start closer to the ground. There have been some trends in this direction, such as courses in finite mathematics and in probability, but there is room for much more. He wrote this in 1990, when NCTM in the US was looking at standards and trying to come up with. But I think, 23 years, we have made very little headway. And of course, I am part of this evangelical group pushing for a lot of finite mathematics, discrete stuff, combinatorics, probability, from a very early age on, bringing in algorithms and so on. But even if, he is probably more into probability, it doesn't matter. But it's clear that somewhere these, topics closer to the ground, which can come from applications, have to come in. And I think we are very far from that. Oh, this is not easy, okay. So let me again end with one more quote which I like from Hans Freudenthal, where he says, children should repeat the learning process of mankind, not as it factually took place, right? When you learn science, you want to rediscover science, but not, but rather as it would have done if people in the past had known a bit more of what we know now, right? You go back to the Greeks, but equip the Greeks with, the Riemann hypothesis and think of, and then it, falls into place. The pupil himself should reinvent the mathematics. And during this process, the learner is engaged in an activity where experience is described, organized, and interpreted by mathematical means. This activity is mathematizing. So I think that's a good place for me to end, to say that the goal of all our mathematical education should be mathematizing thought, whatever that means. Thank you.